In this video, I'm going to demonstrate how ARP is used and how MAC address tables are updated. I want to specifically concentrate on how traffic is sent from router 1 acting as PC1 through a layer 2 switch to its default gateway, which is router 2, how the traffic is routed from one physical interface to another, sent through another layer 2 switch and on to router 3 acting as PC2. These devices have just booted up and no configuration has been done. So as an example, on router 1 acting as PC1, all the interfaces have been shut down. So as an example, show IP interface brief. Fast Ethernet 00 is shut down, and the same is true on the other routers. On switch 1, I'll change the name of the switch to switch 1, but it also has no configuration. Show MAC address table shows that no MAC addresses have been learnt by switch 1 on the left, and the same thing is true for switch 2. Show MAC address table. No MAC addresses have been learnt because the router interfaces are shut down, and hence the switch doesn't learn any MAC addresses from those routers. On router 1, I'll change the MAC address to make it easier to read. So I'll change it to a MAC address such as the following, ending in 0001 to indicate router 1. On router 2, I'll do something similar, but we'll change the MAC address to 2. And then on the Fast Ethernet side, we'll change it to 3. So do show run Fast Ethernet 00. MAC address on this side is ending in 0002. And on this side, it ends in 0003. So on router 3, do something similar. MAC address ends in 4 in this example. And what I'll do now is no shut the interfaces on the routers. No IP addresses have been configured at the moment, but the switches may learn MAC addresses, as you can see here, based on traffic that was sent by the routers. The routers, as an example, will be sending CDP messages and other messages. So switch 1 has learnt that MAC address 1 is on gigabit 00, MAC address 2 is on gigabit 01. Switch 2 has learnt that MAC address 3 is on gigabit 00, MAC address ending in 04 is on gigabit 01. What I'm going to do is start some Wireshark captures here so that we can see what's going on. So Wireshark capture this side as well as this side. So this is the interface on the left. We can see CDP, spanning tree information. As an example, we can see a loop message from this interface, which is used by the router to make sure that the link is up. We can see something similar on this interface. There's a loop message from this interface. So traffic is now being sent. But what I'll do now is configure an IP address on router 1. So that's this IP address over here. And I'll configure IP addresses on router 2 as per the diagram. So that's Fast Ethernet 00. Here's Fast Ethernet 01. And I'll do something similar on router 3. IP address 10.1.2.1. So IP address is configured on router 3. IP addresses are configured on router 2. And IP address is configured on router 1. So if router 1 pings router 2, and I'm going to repeat this twice. Notice we get one timeout and one successful message. In Wireshark, I'll filter for ARP. And what you'll notice is that router 1 sent a broadcast So there's the MAC address of router 1 sending a broadcast requesting the MAC address of a host that has this IP address, 10.1.1.254, which is router 2. Router 2 replies, so notice router 2, 02, replies to 01, indicating what its MAC address is. So the first message from router 1 to router 2 was a broadcast. Router 1 doesn't know the MAC address of router 2, so it sends a broadcast onto the local segment. The switch floods that broadcast, so it arrives on this interface where we're running Wireshark and is received by router 2. Router 2 then sends back a unicast reply to router 1, indicating what its MAC address is. So Cisco Incorporated is the vendor code, and the unique identifier is 02. So router 1 has ARP for router 2's address, and then when we search for ICMP, we can see that there was one successful ICMP message. Due to the delay of the ARP reply, the first ICMP message didn't make it. So we see a ICMP message from 10.1.1.1 to 10.1.254. We can see the source MAC address and destination MAC address. It's a unicast, and we can see that it's a ping request, and then here is a ping reply. Now on this side, we don't see those ARP messages. A broadcast from router 1 to router 2 is killed by router 2. It's not forwarded on. Broadcasts are not forwarded by routers. So as an example, here's the ARP. It's a broadcast. It was received by router 2, but is not forwarded onto this part of the network. The ICMP messages are also contained to this part of the network because the message was sent from router 1 to router 2, not on to router 3. So the ARP message is contained here. On switch 1, the MAC address table shows the two MAC addresses of the two devices. On router 1, show ARP shows us that the local router has this MAC address in its ARP cache that's not going to time out, but it also has this entry in its ARP cache, and it's been in the ARP cache for 3 minutes. So router 1 learnt this MAC address by sending an ARP request out and then receiving a response from router 2. Router 2 in its ARP cache shows that it has this entry for router 1, and it has these two local entries for its two interfaces, F0/0 and F0/1. So it has 3 entries in its ARP cache. It doesn't have an entry for router 3 because no traffic has been sent from router 2 to router 3 and vice versa. These two switches are pure layer 2 switches. They haven't been configured with any VLANs. They're simply switching traffic from one port to another. So what happens now when router 1 pings router 3? So let's do a test where router 1 pings router 3. Ping 10.1.2.1. The pings are failing. Let's have a look at the ARP entries. So at the moment, we are not seeing any ARP messages being sent. We're not seeing any ICMP messages for 10.1.2.1. And that's because this device doesn't have a route in its routing table or a default gateway configured to tell it to forward traffic to router 2. So what I'll do is I'll configure a default route pointing to router 2, and I'll need to do something similar on router 3 to allow the traffic to come back again. So we'll create a default route to 10.1.2.254. That essentially means that router 3, when it doesn't know where to forward traffic, is going to forward it to router 2. So its gateway of last resort or default gateway is 10.1.2.254, and router 1's gateway of last resort or default gateway is 10.1.1.254. So router 1 and router 3 are now configured to point to router 2 for any networks that are not directly connected to them. So ping 10.1.2.1. We lose a ping, and then we have 4 successful pings. So what does Wireshark look like on the left-hand side of our network and the right-hand side of our network? Let's do a search for ARP on both sides. Now these are the ARP messages that we saw previously. The router on the left didn't have to send an ARP message to router 2 because its ARP cache was already populated. Notice this timer has increased. So router 1 already knows what the MAC address is of router 2. But router 2 didn't know what the MAC address was of router 3 previously. Previously, when we used the show ARP command, we only saw an entry for router 1 and the local entries. But now if we do show ARP, notice we see an additional IP address and MAC address in the ARP cache. And that's because router 2 sent an ARP message out saying who has IP address 10.1.2.1. So we can see the source MAC address is router 2, this interface. It's a broadcast. It's an ARP request asking for the MAC address of this IP address. In this case, router 3 replied. It's a unicast from router 3 to router 2 stating that this is its MAC address. And because of that, the ICMP messages from 10.1.1.1 to 10.1.2.1 can succeed. So there is the ping request on this side. There's the response on this side. And here is the ping request over here and the ping response over here. So the pings succeed, but now we need to look at the MAC addresses. So in the Ethernet frame that was sent here to router 2, notice the source IP address is 10.1.1.1 and the destination address is 10.1.2.1. In other words, it's router 1 talking to router 3. The source MAC address is router 1, but notice the destination MAC address is router 2. In the Ethernet frame that's sent on this part of the wire, the source MAC address is router 1, destination MAC address is router 2. And that'll be true over here and over here. And I'll do an additional Wireshark capture in a moment to show you that. But notice the source MAC address is router 1, destination MAC address is router 2, whereas over here, the router changes the MAC addresses. The source MAC address is router 2's interface over here, and the destination MAC address is router 3, acting as PC2. So the MAC addresses were changed by router 2 when the traffic was sent out of this interface. But notice the source and destination IP addresses remained the same. On a per hop basis, when you go across a router or a layer 3 switch, in other words, a switch acting as a router, the MAC addresses are changed. Whenever you go from one VLAN to another, or are physically moved from one interface to another on a router, the MAC addresses are rewritten by the router. The source and destination IP addresses remain the same unless you've implemented a protocol such as Network Address Translation or NAT. I'm going to stop the Wireshark captures and let's run them again. So that you can see how the MAC addresses are rewritten. So I'm going to start 2 captures here and 2 captures here. The switches in this topology are once again simple layer 2 switches. They are not doing any rewriting of frames. They are only layer 2 switches with no layer 3 capability enabled on them. So router 1, ARP cache is populated, ping, router 3, and I'll repeat that once. Ping succeeds. So successful ping was sent and received. ICMP over here. This is the frame that was sent and the frame that was received. So frame that was sent over here is from router 1 to router 2. The same is true between the switch and router 2. Source MAC address is router 1. Destination MAC address is router 2. Over here, however, so firstly, on the left-hand side of switch 2, source MAC address is router 2. Destination MAC address is router 3. Same over here. Source MAC address is router 3. This interface, destination MAC address is router 3. For the return traffic, over here, source MAC address is router 3, acting as our PC. Destination MAC address is router 2, in other words, this interface. On this link, return traffic is the same. Source MAC address is router 3, destination MAC address is router 2. A layer 2 switch is not rewriting MAC addresses, it's simply forwarding the frames on based on the MAC address table. Over here, however, the return traffic is now from source MAC address of router 2 to destination MAC address of router 1. And the same is true over here. Source MAC address is router 2, destination MAC address is router 1. So to summarize, the MAC address in this direction on both this link and this link is source MAC address router 1, destination MAC address router 2. On this link and this link, source MAC address is router 2, destination MAC address is router 3, for traffic going from left to right. On the return, source MAC address over here is router 3 going to router 2. Over here it's router 2 going to router 1. IP addresses stay the same throughout because we're not using NAT. So this is the example over here, and this is the output over here. The MAC addresses change at every hop when you go across a layer 3 router or a layer 3 switch, and you're doing inter-VLAN routing, but the IP addresses stay the same. MAC addresses are changed, IP addresses are not changed. Now, for how long is the information contained in the ARP cache? You can see this has been there for 18 minutes. That depends on the device, but notice show interface F0/0 shows us that the ARP timeout is 4 hours, and that's a default on a lot of Cisco devices. So show interface F0/0 on router 2. ARP timeout is 4 hours. Now I'll save these routers configurations and then reboot them, and what you'll notice then is that they will have to rebuild their ARP cache. So I'll reload the 3 routers, and they've now rebooted. Show IP interface brief. IP address of this device is 10.1.1.1. Show ARP. Notice it only has its local entry. It doesn't have an entry for router 2. Show ARP on router 2 only has local entries. Show ARP on router 3 only has a local entry. What I'll do is restart the Wireshark captures. And what we should see is router 1 ARPing for router 2 and router 2 ARPing for router 3 when we do a ping. So on router 1, ping 10.1.2.1, and I'll repeat it only twice. Okay, at that point it still failed, but then we got successful messages after that. So it took a bit longer than a single ping. On the Wireshark capture over here, filter for ARP. There's the broadcast. Now, even though router 1 is pinging router 3, notice it's ARPing for its default gateway. So that will be true here as well as here. So this is the link here. And if we filter for ARP, Notice the ARP request is for the MAC address of router 2, not the MAC address of router 3. When traffic is sent from one subnet to another subnet, the traffic needs to go via the default gateway. So the local PC or router is going to ARP for its default gateway's MAC address. Hence, the ARP shown over here is for router 1 ARPing for router 2's MAC address. So what about over here? Filter for ARP. Router 2 is sending a broadcast, and it's ARPing for the MAC address of router 3 because this device is local on this subnet. If there was another router in between here, router 2 would ARP for that router's MAC address, and the MAC addresses would be rewritten again. But in this case, because we only have a single router, the MAC address rewriting takes place once. On this interface, it's the same ARP. Router 2 is ARPing for the MAC address of router 3. ARP entries are once again stored in an ARP cache. They time out by default on a lot of Cisco devices after 4 hours. So there's the router. Here's the switch. Notice ARP timeout 4 hours. In some cases, you have to change that ARP cache value, especially when using HSRP, which we'll discuss later in the course.